Can you hear me at the back? Yeah. So good evening, everyone, and welcome to the Institute lecture. So we are very happy to have with us Professor Joachim Kopp. So Joachim is a professor at the Johannes Gutenberg University at Mainz. A little bit of intro about him. So Joachim obtained his PhD from the University of Heidelberg in 2009, and then he held research positions at Fermilab and Heidelberg before moving back to Mainz in 2014. In 2009, he was awarded the Otto Hahn Award of the German Max Planck Society. And then in 2014, he won a prestigious ERC grant. So Joachim is a leading expert on neutrino physics. He has worked on a large number of topics in theoretical particle physics, of which neutrino physics stands out as one of the pillars, and this is what he's going to tell us about. Apart from this, he has also written a number of influential papers on dark matter, which, as you also know, is another one of the bigger pillars of particle physics as well. And not only that, he has also carried out pioneering work on quantum sensing in astroparticle physics, with the particular focus on the detection of gravitational waves, which is another very exciting area that's happening nowadays. So from 2018 to 2025, Joachim also held a research staff position at CERN, which is, as you all know, is the largest particle physics lab in the world. And there he also led the theory activities of the CERN Neutrino platform, and also the Quantum Technology Initiative platform as well. So today he will be telling us about what are the current challenges and opportunities in neutrino physics. And just to give you a little bit of extra information, Joachim is visiting us at the Department of Physics for this entire week, and he'll be around till Friday. So I'm sure there will be a lot of questions at the end of the talk, but in case you have more questions and you run out of time, feel free to visit us in the department, and we'll be happy to have more of a conversation and chat with him. So with this, I'll not take up more time. I'll invite Joachim on the stage and let him talk about this topic.
Okay. Yeah, thank you very much for the kind invitation. It's now my third time in Mumbai, and it's always a pleasure to be here. And thank you all for coming. Yeah, so as Manibrata announced, my plan here is to talk a bit about the current status of neutrino physics. And to give a metaphor of what the current status of neutrino physics is, let me start with a picture that has nothing to do with neutrino physics, but with a beach somewhere in Scotland. So a couple of years ago, I was in this area with my family, and so my kids went to the beach, and they looked for clamshells, and they found a particularly nice clamshell, so there was a lot of excitement about it. And so they started looking for more, and indeed they found more, and they noticed that they come in different colors, in different sizes, slightly different shapes. So they started asking questions about them. And they were wondering, for instance, why these clamshells were to be found around the UK and the Atlantic coast of Europe, but not in other parts of Europe, also other beaches that they had been to. Well, and finally the days went on, the clamshells were forgotten, but of course we could not throw them away, so we had to make sure we could package them in such a way that we could transport them home. So overall the clamshells became a bit of a nuisance in the end. And I think that's very much the same for many discoveries in particle physics. So there is an early stage of discovery where everyone is very excited about the new thing that was found, followed by an area of precision where the new thing is studied in great detail, followed by an era where the new thing is used as a messenger to learn about other things. So for instance, neutrinos are being used as messengers these days. Well, and finally, today's signal is tomorrow's background, so in the end, most things become a sort of a nuisance. And in neutrino physics, that analogy certainly works. So the era of the first discoveries in neutrino physics has happened already in the second half of the 20th century, when the neutrinos were first detected, and then later on, some of their more exotic properties were detected. We are now in the era of precision physics, where the goal is really to understand neutrinos with the utmost precision, possibly uncovering small deviations from the way we think they should behave, and thereby learning even more. Simultaneously, neutrinos are being used as messengers because we figured out how to observe neutrinos from astrophysical sources. And by doing that, we can not only learn about neutrinos, but we can also learn about astrophysics. So that's a big topic these days. But on the other hand, neutrinos are already becoming a bit of a nuisance as well if you want to look for things that are even harder to detect than neutrinos, such as dark matter. So just last year, experiments looking for dark matter had for the first time run into an unavoidable background due to neutrinos. Now in this talk, I want to talk especially here about the precision, messenger, and nuisance aspects of neutrinos, starting with precision physics. So what is precision neutrino physics about, and why is that a thing that's interesting? Now, to some extent, precision neutrino physics comes about because, well, neutrinos are leptons, and people studying leptons are very jealous of people studying quarks, because quarks have been studied for much longer than neutrinos, and in particular, their properties, or at least many of their properties, can be summarized in a plot like this. So this is one way of representing the Kabibo-Kobayashi-Maskawa matrix that describes the interrelations between the three generations of quarks in the standard model of elementary particle physics. Now for this talk, it doesn't matter what exactly these quantities are, but what I want to show here is that all these different colored bands stem from different measurement campaigns. And so you see how they all beautifully meet in this tiny little area here. So what this means is that first of all the measurements agree, and second, it means that taken together, they constrain the parameters shown here to a very narrow window. So they've reached incredible precision. Now we can do something similar for neutrinos. This is the equivalent plot for neutrinos, and if you look at it, it looks far more messy. So what is a tiny little region here in the quark sector is still a relatively broad circular region in the lepton sector. So clearly we understand leptons far less well than we understand quarks. And there are reasons to try and remedy this. Okay, so when I say that the plots I've just shown show the relations between the quarks and leptons, we first have to understand what these particles are in the first place. So here's a sketch of the known zoo of elementary particles. We have up here the 6 quarks, up, down, charm, strange, top, and bottom. Ordinary matter essentially consists mostly of up and down quarks. And of electrons. Electrons fall in the category of charged leptons. And like the quarks have heavier siblings, so does the electron have 2 heavier siblings, the muon and the tau. And each of these comes with a neutrino. So there is 3 different types of neutrinos, or as we say in particle physics, 3 flavors of neutrinos, which we call the electron neutrino, the muon neutrino, and the tau neutrino. And those are the ones that this talk is mostly going to be about. Of course, all of this, this picture can also be turned into equations. Here is, for instance, the equation that describes the behavior of neutrinos in the standard model of particle physics. But instead of looking at this equation, it's often much easier to represent the equation again by a type of Feynman diagram. For instance, these 2 diagrams here show the main interactions of neutrinos. So there's on the one hand this vertex through which a W boson, so one of the weak gauge bosons, couples to an electron and a neutrino, and on the other hand also the Z boson can couple to 2 neutrinos. Now, one thing that is special about well, both neutrinos and quarks is that what we call the flavor neutrino, so what I called the electron neutrino, the muon, and the tau neutrino, they do not have a definite mass. Rather, they are quantum mechanical superpositions of states that do have a definite mass. So this can be written in this way. The flavor, the so-called flavor eigenstate, which is the state that has well-defined couplings. For instance, the electron neutrino is defined as the neutrino species that likes to interact with electrons. The muon neutrino is the one that interacts with muons, and so on. So each of these can be written as a superposition of 3 so-called mass eigenstates. And the relation between the mass and flavor eigenstates is given by a unitary 3x3 matrix. So it's just a change of basis in the Hilbert space, and depending on what we want to calculate, it's sometimes more convenient to work in the flavor basis, sometimes more convenient to work in the mass basis. Now this unitary 3x3 matrix, that's clearly central then to our understanding of neutrinos. And a general way of parameterizing such a matrix is to write it as a product of three two-dimensional rotation matrices. So what this notation here means, so S23 means the sine of an angle which we call theta 23 in the 2-3 plane. S13 is the sine of an angle acting in the 1-3 plane, and 1-2 is then the angle in the 1-2 plane. So there is three mixing angles here, and in addition, one of these three matrices can also have a complex phase. So 4 parameters, that's what it takes to parameterize this matrix. Now you might say, well, a general unitary matrix can have more than 4 parameters, but one can show that all the other parameters are unphysical, so they can be absorbed into redefinitions of the corresponding quantum fields. So those are the 4 physical parameters, and we have no way of determining them from first principles, so we have to measure them. And that's what much of what I call precision neutrino physics is about. We already know a bit about them. For instance, we know that there's one mixing angle which is very large, maybe even maximal. There's one mixing angle which we have well measured. There was just another new measurement from a new experiment that appeared just today. We know it's large, but we also know it's not maximal, but somewhere in between. And then there's one mixing angle that is small but non-negligible. So at the moment we have measurements, but there's no clear pattern. So basically, if you were to draw random numbers for these mixing angles, that's a very likely pattern that you would find. Well, and this complex phase, we know hardly anything about it. But it has crucial consequences for nothing less than the evolution of the universe, perhaps. Okay, yeah, and so what this plot here that I showed before, what this essentially summarizes is our current knowledge about the mixing angles and this complex phase. The fact that this is still a circle is a reflection of the fact that we don't know the complex phase, because the complex phase basically tells you where you are along the circle. The mixing angles tell you where you are along the width of this circle. Okay, now how do we probe those parameters? The phenomenon that we are exploiting there is what is called neutrino oscillations. So what are neutrino oscillations? So I showed you that the neutrino mass eigenstates and the neutrino flavor eigenstates are not the same. So, but the flavor eigenstates, that's how neutrinos interact. So if we make a neutrino in an experiment, we produce it in a flavor eigenstate. Now, the propagation of neutrinos, though, depends on their energy and therefore on their mass. So when I produce this flavor eigenstate, what I'm effectively creating is a superposition of 3 mass eigenstates. And those 3 mass eigenstates propagate slightly differently. So they acquire different complex phases during propagation. And then when I detect the neutrino, I project them back onto a flavor eigenstate, which means that I can see these complex phases as kind of an interference pattern. And this interference pattern is what we call neutrino oscillations. What it means phenomenologically is if I start, for instance, with a pure muon type neutrino, then over time that muon neutrino will acquire a component that behaves like an electron neutrino, then it will go back to being a muon neutrino, then it might go back to an electron neutrino, and so back and forth periodically. And by precisely studying this phenomenon, one can then infer with a little bit of algebra the values of these mixing parameters. Now, how does one do this? The most precise tools we have at the moment are so-called long baseline neutrino oscillation experiments. And these are quite large facilities, and obviously they start with a neutrino source. So we need a way of making neutrinos. And one way of doing this is by using a particle accelerator. If you take a particle accelerator, you accelerate protons, a very high intense beam of protons, to a high energy, and then you dump those protons onto a block of material, onto a fixed target. You get lots and lots of intermediate particles called pions, and those pions then decay further to neutrinos. So that's how you effectively create a neutrino beam. and then you detect this neutrino beam some distance away. So for the example I'm showing here, that distance is, for instance, 1,300 kilometers. And the reason it needs to be such a large distance is because you need to give the neutrinos time to oscillate. So as you've seen on the previous slide, this is a time-dependent phenomenon. So if you want to see the conversion from one flavor to the other, the neutrinos need to have time to undergo these oscillations, so they need to travel they need to travel sufficiently far. And they are traveling at the speed of light, so time and distance are essentially equivalent. Okay, and but of course, because the neutrinos are then so far away, the beam gets diluted a bit. So in order to still detect anything, you need gigantic detectors. So we are talking here about detectors that have masses that are measured in tens to hundreds of kilotons of material. And finally, like any experiment, also this experiment comes with systematic uncertainties. In particular, the neutrino beam is theoretically not so well understood. So to circumvent this, what one does is one has a set of near detectors which are located closer to the source to measure the unoscillated beam. So there's one set of detectors that measures the neutrinos before they oscillate, and then another set of detectors that measures the neutrinos when they have oscillated. And of course, in the end, you still catch only relatively few neutrinos. As you know, neutrinos interact very, very weakly. So in order to catch any, you need these gigantic detectors, and still, by far, the most of the neutrinos that you produce will just go through the detector unimpeded. But from time to time, you catch one, and those are the ones that you use to do physics with. Okay, now for this particular experiment that I've shown here, that's an experiment that's being built in the United States. There's a similar experiment also being built in Japan. So this is what it looks like. In this case, this experiment is located in a rural area called the Black Hills. Here you see old head frames from the mining days of this region. And the reason it's in a mining town is because the detector is placed deep underground. So this is what the cavern looks like that will eventually house the detector. So here's a person for scale. So you see that these are really gigantic caverns, and therefore that will house gigantic detectors. The reason it needs to be so deep underground is in order to shield it from environmental noise, in particular from cosmic rays. Okay. This is a small-scale mock-up of what the detectors will look like. And small scale here means still fairly big. So there's, again, some people for scale. And this is, I think, it's half as wide, half as high, and 1/6 as long as one of the final far detector modules will be. So that's basically a prototype being built at CERN at the moment, or being operated at CERN. This is what it looks like from the inside. You sometimes see these pictures and you think, oh wow, that detector is golden on the inside, but no, it's actually just silver. It's just stainless steel. It's just a stainless steel vessel. The reason it looks golden is because it has yellow light in it, and that's because the detector has some optical components and they would get damaged by white light, so you need to use yellow light. And what this effectively is it's a gigantic cryostat that will be filled with liquid argon. So the detection material is liquid argon. And then this is what it looks like when the actual detector is installed in the cryostat. And here you don't see very much. You see these rods here, which are essentially there to shape the electric field, because what this effectively is a time projection chamber. Okay, I won't have time to go into detail on how exactly it works, but suffice to say that this is an excellent way of precisely reconstruct neutrino interactions. Okay, so as you can clearly see, people are going to a lot of effort to undergo this. So let's reflect. Let's take a step back and ask ourselves, okay, why do we do this? So I've said, well, measuring something very precisely is, of course, interesting, but it's often not a goal in itself. So why is it interesting to measure so precisely the properties of neutrinos? Well, one reason is that there is the possibility of a phenomenon called leptonic CP violation. And what that effectively means is that neutrinos and antineutrinos do not behave in exactly the same way, or might not behave in exactly the same way. We don't know if they do or not. And why is that interesting? That's interesting because there's a possible connection between such a non-equivalence between neutrinos and antineutrinos and what we call baryogenesis. Now, baryogenesis refers to the question of why there is more matter and antimatter in the universe. And that's a very central question to our very existence, because according to the current best theories of particle physics that we have, the early universe, the Big Bang, should have produced matter and antimatter in equal amounts, and then as the universe cooled down, the matter and the antimatter should have annihilated away. So there should be nothing left out of which we, or planets, or stars, or anything could consist. So there must have been a slight imbalance between matter and antimatter in the early universe. And it's not clear at the moment how that slight imbalance was produced. But as I said, it's crucial because the little bit of matter that there was more than antimatter, that's what we are made of. That's what everything that we observe is made of. And it's possible that this slight asymmetry between neutrinos and antineutrinos could be at the origin of this phenomenon. And while studying neutrino oscillations very precisely will not provide the ultimate answer on whether or not this is indeed the case, it will at least give us hints in the right direction and where to look further. Then when we study the standard model very precisely, we do so always because we hope to find a deviation. So the hope is that neutrinos will eventually be a portal to physics beyond the standard model and tell us what the missing pieces in our understanding of particle physics are. Finally, I already mentioned in the beginning that neutrinos have turned out to be very versatile astrophysical messengers. But of course, if you want to use them as a messenger, you first need to understand them themselves. Finally, what I call hints for the origin of flavor here, that has to do with the fact that, remember I showed you this diagram of how we sorted the known elementary particles into 3 generations. But to be honest, we have no idea why elementary particles follow that structure. We have no idea why the parameters of that mixing matrix are what they are. We have no idea why the masses of elementary particles seem to follow certain patterns. And the hope is that understanding neutrinos more precisely might shed some more light onto this question. Well, and finally, the detectors that we are building to study neutrinos very precisely, they are actually not single-purpose detectors, but multi-purpose observatories that offer lots of secondary opportunities as well. For instance, they allow us to study things like supernovae. They allow us to study for other new particles beyond the standard model that might have nothing to do with neutrinos. They might allow us to look for proton decay and hints for grand unified theories. Okay, now there is one big problem in this endeavor. I already alluded to it when I explained why we need those near detectors, so why we need to measure the unoscillated flux because we can't calculate it. And that has to do with the fact that it's very hard to understand how neutrinos interact with ordinary matter. Now, why is that? Why is that so hard? So let's look first at an interaction between a neutrino and a nucleon. So a typical detection process in a neutrino detector is of this form. You have, say, a neutrino coming in, converting into a charged lepton. So here, for instance, a muon neutrino converting into a muon. And it does so by interacting with a neutron that in the process gets converted into a proton. Okay, now that sounds simple enough. But the problem is that essentially by doing this, the neutrino feels the structure of this nucleon. So at energies of maybe hundreds of MeV or so, this process can be understood as quasi-elastic scattering. So that means the neutrino basically sees the nucleon as one entity. It's unable to resolve the substructure of the nucleon. It might feel the substructure of the nucleon through so-called form factors, and that's already a first source of uncertainty. But things get even more complicated when we go to higher energies, because at higher energies, neutrinos are able to excite the proton. So like an atom, also the proton has excited states. The most important one is the so-called delta resonance. So the interaction with the neutrino can create such an excited state of the proton, and then that delta resonance then again decays typically to a pion and another nucleon. So we need to understand the cross-sections for the production of these resonances. This is physics of the strong interaction in the non-perturbative regime, so it's impossible to calculate anything from first principles there. Finally, at higher energies, things get a little easier again because the neutrinos essentially fully resolve the substructure of the proton and scatter on individual quarks. But now this was for scattering on a free nucleon. It gets far more complicated than this because those nucleons are typically bound inside an atomic nucleus. So that means, first of all, that we need to understand the initial state of that nucleon. So the nucleons inside a nucleus can be viewed as particles bound inside a potential well. And as you know, when particles are bound inside a potential well, then even when they are in the ground state, they have a non-zero momentum. And the nucleus is a very small potential well, so that momentum can be fairly large. And so ideally, we would need to fully understand the wave functions of the nucleons inside the nucleus. And again, this is physics of the strong interaction in the non-perturbative regime, so clearly we can't have that understanding. But it would be crucial to do so because if a neutrino scatters on a nucleon at rest, the kinematics is very different from when the neutrino scatters on a nucleon that already comes in with a large momentum. Then the nucleons are not on their own because they are strongly bound to each other, which means they interchange pions all the time. So sometimes when a neutrino comes in, what it sees is not really a single nucleon, but it sees two nucleons at the same time. So in a sense, it's scattering on two nucleons at the same time. Or viewed another way, while the neutrino is interacting with the first nucleon, that nucleon is exchanging a pion with the second nucleon. And then these intranucleon correlations come in, and we get a class of processes that's very difficult to treat, which are called so-called two-particle, two-hole processes. Well, and then finally, after all this messy interaction is over, and we have some interaction products, these interaction products are still located inside an atomic nucleus and need to propagate out. And lots of things can happen to them on the way out. They can scatter on other nucleons. They can be absorbed. They can trigger further reactions inside the nucleus. And all of that needs to be modeled as accurately as possible to understand how neutrinos interact. So this is where at the moment, one of the main limitations of precision neutrino physics lies. Okay, let's switch topics a little bit and talk about neutrinos as messengers. I've already emphasized on a couple of occasions that neutrinos are excellent astrophysical messengers, and in fact they've been so for more than half a century. So soon after the neutrino was discovered in a terrestrial experiment at a nuclear reactor, which is a very abundant neutrino source, also neutrinos from the sun were detected. The sun, again, is a super abundant neutrino source because there's lots of nuclear reactions going on in the sun, and typically nuclear reactions that involve the weak nuclear force, that's what creates neutrinos. Now, since then, these solar neutrinos have kept people quite confused for a few decades, but by now we think we more or less understand them, and we can use them to learn a lot about what's going on the inside of the sun. Because with normal observations of the sun, if we look at the sun in the electromagnetic spectrum, what we are observing is the surface of the sun. Whereas the neutrinos are coming from its very core. So with the neutrinos, we can look into the very inside of the sun. And while a photon, so when you produce a photon at the core of the sun, by the time that photon gets emitted from the sun, that's 1,000 years later, because photons diffuse out. They can't propagate freely because the material is so dense, so they diffuse out, and the time scale for diffusion from the center of the sun to the outskirts is 1,000 years. Whereas neutrinos come out right away. In 1987, we got lucky. We observed neutrinos from a supernova. So a supernova is the explosion of a massive star that has reached the end of its life. And those neutrinos, so people are still, there were 20-something neutrinos that were observed at the time, and people are still writing papers about those. So that was one of the most important events in astroparticle physics of all time. And the reason it's so important is, for instance, because it allows us to see what's going on inside a supernova, so inside one of the most extreme environments that exist in the universe. For instance, it teaches us about the formation of heavy nuclei, the so-called nucleosynthesis. It teaches us in general about how matter behaves under extreme conditions. Now, more recently, we've observed neutrinos at incredibly high energies coming from very distant cosmic particle accelerators. And when I say high energy here, I mean energies hundreds of tera electron volts up to peta electron volts. And recently there was an event that has presumably an energy of order 200 PeV even. And the reason this is interesting is because it allows us to get a glimpse of where such ultra-high energy cosmic rays are produced. So typically this has something to do with the physics of supermassive black holes. Now, neutrinos play a crucial role for the evolution of the early universe. I can't go into this in great detail, but yeah, to understand how the universe evolved during, say, the first few minutes of its life, and then how structures in the universe formed, neutrinos play a crucial role there. And finally, neutron stars are interesting neutrino sources. Now here, I would like to focus on one of these aspects, and to show you which one this is, let's have a look at this picture here. That's a picture of some part of the Large Magellanic Cloud, and the arrow here points to a rather unassuming star named Sandulik -69 + 202. And so that star, it sounds totally uninteresting, and it probably was totally uninteresting until 1987, because 1987 was when that star exploded. It exploded in what's called a core collapse supernova that then got labeled supernova 9087A because it was the first one observed in 1987. And the reason it's so interesting, because it's fairly nearby. So it's not immediately in our galaxy, but it's in the Large Magellanic Cloud, which is one of the satellite galaxies that are orbiting the Milky Way. So still basically in our galactic backyard. And that meant it was close enough to observe a neutrino signal. Now, how does that work? So when such a massive star runs out of fuel, its core collapses. You can imagine massive stars, so there's a huge gravitational force that tries to pull the material inside. But as long as nuclear fusion is going on in that star, there is a counteracting force, namely radiation pressure. So the nuclear fusion creates a lot of heat, which creates pressure that counterbalances gravity. And so that leads to stars being stable. But at some point, the star has burned all its fuel, so the thermal pressure suddenly disappears, and there's nothing that can counteract gravity, and so the core of the star collapses into a neutron star. So the material suddenly becomes denser than nuclear matter. And when that happens, so there's lots of material falling onto a neutron star that has a radius of only maybe 10 to 15 kilometers or so. So there's a gigantic release of gravitational energy. For instance, when a proton falls onto a neutron star, typically the amount of energy it releases is 1/10 of the proton mass. And now imagine how many protons there are in a star. So there's really an enormous release of energy. And that enormous release of energy leads to an enormous explosion, because that part of it gets converted into kinetic energy that just drives the outer layers of the star away. And therefore, when such a star explodes, it becomes brighter than the rest of its galaxy. So a single star is then brighter than an entire galaxy containing billions of stars. But these photons, so this massive burst of photons that's brighter than a whole galaxy, that is 0.01% of the energy release in a supernova. About 1% goes into kinetic energy. Somehow the labels have disappeared, sorry. So there's about 1% that goes into kinetic energy. That's what you can see here. The photons you can't even see because the slice is too small. There is about 1% that goes into kinetic energy. That's what drives the explosion. And 99% go into neutrinos. Again, the label is missing, but this is supposed to be neutrinos. So clearly, most of the energy goes into neutrinos. So by looking at those neutrinos, we can learn a great deal about how supernovae work. Here is what the neutrino signal from 1987 looked like. So this is neutrino events plotted here as a function of time and as a function of energy. So you see the whole thing lasted about 10 seconds. That's about what we expect. The largest flux of neutrinos comes during the early stages of the supernova, and then gradually it peters out over those 10 seconds. Now that was in 1987, and the supernova was not directly in our galaxy, but only in one of the satellite galaxies. Now, when the next galactic supernova happens, we expect a far greater signal. We don't know when that will be. The rate is about maybe 1 per century, maybe if we're really lucky 2 per century. So I would say we have a non-negligible chance that each of us will still see one within our lifetimes, but it's not guaranteed. But when it happens, it will be quite spectacular. We expect, with modern neutrino detectors, we expect at least tens of thousands of events from such a supernova. And clearly, this allows us not just to draw such a scatter plot with a few events on it, but it allows us to draw a detailed light curve. It allows us to draw detailed neutrino spectra, and to do all of this separately for the different neutrino flavors. So there's really a tremendous amount of information that will be contained in that signal. Okay, but there's one problem, and that problem has to do with the flavor composition. And that's because we kind of understand how neutrinos are emitted at the very core of the supernova, but then we've seen before that neutrinos oscillate as they propagate. And inside a supernova, these oscillations are far more complicated than in a terrestrial experiment. And that is because each neutrino feels the presence of all the other neutrinos. Now, to understand that, we have to think about how neutrinos propagate through matter. Let's first talk about how neutrinos propagate through ordinary matter. You've seen those diagrams before. Neutrinos can scatter on an electron, a proton, or a neutron through the exchange of a Z boson. And if it's an electron neutrino, it can also exchange a W boson with an electron. Now, in general, those scatterings are very rare. As you know, neutrinos interact very weakly. So in order to really get an order 1 probability for a neutrino to interact, you would need an absorber that's about the size of the Milky Way. However, there is one process where this is important, and this is so-called coherent forward scattering. So coherent forward scattering means you exchange a force carrier without exchanging any momentum. In other words, you go in with, say, a neutrino and an electron that have certain momenta. They exchange a W or Z boson, but the outgoing neutrino and electron have exactly the same momenta again. So their quantum state has not changed. They have exchanged a W or Z boson, but their quantum state has not changed. And if their quantum state has not changed, we have no way in principle, first of all, to determine whether such a gauge boson exchange has taken place, and if so, which of the many electrons in the background matter the boson was exchanged with. So in other words, we cannot distinguish, for instance, between a diagram where the neutrino exchanges a gauge boson with the first electron, the diagram where it exchanges one with the second, the third, and so on. And because we cannot distinguish between these possibilities, we need to sum them up coherently. And that means that this process scales not with the number of particles in the background, but it scales with the square of the number of particles in the background. And that is why this process is relevant for neutrino propagation, even though hard scattering processes are not. So that phenomenon is well known and well observed in ordinary matter. It can be understood by adding an extra term to the Hamiltonian that describes neutrino oscillations. And in propagation through ordinary matter, it leads, for instance, to such resonance structures in neutrino oscillations. So what this essentially means is that at particular neutrino energies, the oscillations are particularly pronounced. Now that's in ordinary matter, that's reasonably well understood and experimentally confirmed. For supernova neutrinos, however, there's not only matter effects with ordinary matter, but there is also matter effects with the other neutrinos. And that's theoretically a very hard problem. So one way of describing it is by writing down a von Neumann equation for the neutrino density matrix. So that density matrix, by this I mean basically a 3x3 matrix in flavor space that depends on the position inside the supernova and the momentum. And for neutrinos with a given position and a given momentum, it fully describes their flavor state. It shows the ratios, the flux ratios between different flavors, and how they are their phases are correlated. And then the equation describes how the flavor state of the neutrinos evolves. So obviously there's a time derivative here because we are interested in the timed evolution. There's one term here that describes neutrino propagation, because clearly the density matrix at a given position can change simply because neutrinos move from one place to the other. Now the terms that really encode the most interesting physics are the ones on the right-hand side. There's one term that describes vacuum oscillations, so just ordinary oscillations. There's one term that describes the matter effect, so the interactions with ordinary matter. That's what I explained on the previous slide. And there's one term that describes neutrino self-interactions. And this neutrino self-interaction term, its structure is that it is proportional to the Fermi constant. That's just the normalization factor that describes the strength of the weak interaction in the standard model. But then there is an integral over all neutrino modes. There's an angular factor, and then there is a dependence on the neutrino density matrix itself. So in other words, through this term, each test neutrino feels the presence of all the other neutrinos that happen to be in the same place at the same time. And this term is what makes the evolution highly nonlinear. And therefore, this is not computationally tractable so far. It's a highly nonlinear problem, it's a multi-scale problem, so it's a numerical nightmare. But let me emphasize again, that's a pure standard model problem. So there is no physics beyond the standard model or anything involved here. It's a pure standard model problem, and we'd better understand it, because if we don't understand it by the time the next galactic supernova explodes, then we won't be able to use the data from that supernova in the optimal way. Okay, now there is one aspect to this problem that has recently caused a bit of discussion in the literature, and that is the possible role of quantum entanglement. So you have these neutrinos interacting with each other all the time, so one may wonder whether they get quantum mechanically entangled, and if so, whether that's relevant to their phenomenology. Because if that's the case, then even this computationally intractable equation would not be enough. Because effectively, this is a mean field approach, right? Every test neutrino feels the integrated effect of all the other neutrinos. If entanglement were relevant, then this would not be enough. Then one would really need to study an n neutrino system, and that would mean one would need to track an exponentially large Hamiltonian, which is clearly something that's impossible on classical hardware. And that's where there are a few groups who are studying this problem with the help of quantum computers. So what's the idea here? The idea here is, if the neutrino system were indeed a highly entangled quantum system, and we are not sure it is, but if so, then the best way of simulating it is, well, to simulate it on a highly entangled quantum system. The basic idea is that the flavor state of each neutrino is mapped onto a qubit. So in the simplest case, neglecting the third neutrino flavor and only considering two neutrino flavors, basically the 0 and 1 states of a qubit are mapped onto the electron flavor state and the muon flavor state, for instance. Then the whole system is then the Kronecker product of all the individual qubits, and one can also write down the Hamiltonian. It contains one term that describes vacuum oscillations and one term that describes the neutrino self-interaction. And then the time evolution is usually realized via so-called trotterization, which is nothing but discretization in time. So one applies this Hamiltonian repeatedly in small time steps. We've done some simulations of this type. So here's a reproduction of a phenomenon called collective oscillations, which basically means that neutrinos of different energies oscillate with the same oscillation length in such a system. So that the curves here show the expected result, which is still, this is just a very simple toy system, so there this is still doable even analytically or semi-analytically. And then the data points here are either from a simulated supercomputer or from a real supercomputer. You still see a lot of spread there, which just shows how imperfect current quantum computers are. Here's another toy system. So this is specifically a toy system where one can analytically show that a mean field theory and fully entangled quantum calculation are equivalent. So the dashed curves here show the result from the mean field approach, and the data points show the results for a fully entangled computation on a quantum computer. So you see that basically this agreement is confirmed. Again, this is something that we already knew analytically beforehand, but it's nice to confirm it on real hardware. You also see that we can basically simulate 3 time steps. After 3 time steps, we see deviations here, simply because we run into the noise limit of the quantum computer. Okay, so as I said, to me the crucial question here is for the moment whether the mean field approximation is valid or not. If it's not valid, or if it is established that there are systems where entanglement does play a role, then a quantum simulation would really be the way to go once the hardware allows it. And then one can ask interesting questions. For instance, what is the optimal hardware platform? How does one deal with the errors and the noise on the quantum hardware? And what other applications are there of the algorithms that are being developed for this? Okay. Now, in the last part of my talk, I would like to keep this very, very brief. I have more slides that I'm happy to talk about over coffee or over the next couple of days. I want to briefly mention that, of course, one of our secret hopes is that by carrying out this precision neutrino physics program, we will eventually hit upon some deviations from the standard picture. So the hope is to see something that doesn't fit the standard model of particle physics. Now, just to give you a glimpse of what that could be, as a theoretical physicist, we like to classify new physics in terms of the mass dimension of the operators that it would introduce in our Hamiltonians. At mass dimension 4, there's, for instance, the possibility that there are extra neutrino species. So so far we are working under the assumption that there's 3 neutrino species in nature, but there is the possibility that there is more. Neutrino magnetic moments. So neutrinos obviously don't carry electric charge, but through diagrams of this type, where the neutrino temporarily goes to a charged lepton and a W boson and then back to a neutrino, it can in principle still couple to the photon via this loop. That coupling would constitute a magnetic moment, and in fact the neutrino does have a magnetic moment even in the standard model, but that magnetic moment is super tiny, 5 orders of magnitude beyond our current experimental limits. But in theories beyond the standard model, these neutrino magnetic moments could in principle be enhanced. So the hope is that maybe this is one way to uncovering the existence of new particles. Finally, neutrinos interact with matter in complicated ways, but it's possible that also there is new ways in which neutrinos could interact with matter, again possibly mediated by new heavy particles. Okay, I'm not going to go into details on any of these. I just wanted to show you why I said in the beginning that neutrinos can also be a nuisance. And they can be a nuisance when you want to look for things that are even more difficult to detect than neutrinos, such as dark matter, for instance. So here's a plot that summarizes the status of so-called dark matter direct detection experiments. So these are experiments that look for the extremely rare scattering of a dark matter particle with an atomic nucleus. We don't know if that process exists, but in many theories of dark matter, it is predicted to exist, so we look for it. And all these different curves here show exclusion limits from many different experiments. So simply the sheer number of these curves shows you that this is a very active field of research. But then there's also this ominous region down here, and what this shows is that once experimental sensitivity reaches this region here, then experiments will have to deal with an unavoidable background to neutrinos. Because in the same way as dark matter particles can scatter on atomic nuclei, so can neutrinos scatter on atomic nuclei and mimic the signal of dark matter. And because you can't shield neutrinos, right? You can't build a shielding that absorbs neutrinos. That's a background that is almost impossible to avoid, so one has to deal with it in some way. So for people searching for dark matter, I think it's fair to say that neutrinos are a nuisance. Okay, with that, I would like to come to the end of my talk. I'd like to thank you for your attention during this journey through the 4 stages of neutrino physics. And yeah, thank you for coming. Thank you for your attention. I'm happy to talk more.
Thank you, Joachim, for a very nice talk, ranging from astrophysical scales to the quantum scales. So we'll open up the gallery for questions.
So will you tell us a little bit more about the quantum simulation that you're doing? What does it really entail? Because we don't really have a quantum computer yet, right?
No, this was on real quantum computers. This was done at a quantum computer at IBM that basically anyone can access through the cloud. So IBM, it's a machine. So this was done on a machine that I think has 156 qubits. And is accessible through the cloud. So IBM gives everyone, if you create an account there, you get 10 minutes of quantum computing time for free each month. And this was, so for this, the free tier was just not sufficient. The first plot I showed was actually done using those 10 minutes so this one here, this was done using the 10 minutes that we get for free. The second one that I think required 20 minutes or so. So this was done through a subscription that CERN has, through a contract that CERN has with IBM. But it was done on real quantum hardware. Now the disadvantage is, of course, that hardware is still extremely noisy. So the limitation here was not the number of qubits. This was a simulation, I think, involving only 20 of those 156 qubits. But the problem is really that once you do too many operations of them, you accumulate noise, and that's why you start seeing those deviations. But this was, so the way this works in practice is there's Python packages in which you implement your quantum circuit, and then there's routines that then communicate over the internet with the hardware, submit the job to the hardware, and then depending on how long the queue is, you wait for a bit and you get your result back, and then you can again analyze it in your Python code.
And basically, how long does this process take for you to run, let's say, one of these things on a quantum computer, which the runtime is only like 20 minutes, as you said, or whatever, yeah. But the whole process?
That depends on how fast I am with Python programming. So I think with a bit of experience, for like someone who has experience with that, setting up the circuit is not all that difficult. That's a fairly straightforward process. Then, of course, you try lots of things to try and make it better, to optimize it. That's then what takes time.
No, but I meant on the queue. Like, you probably don't get to run immediately.
It very much depends. So IBM has a number of machines in the queue, and their noise levels fluctuate depending on environmental conditions. So if you want to have at any given time, if you want to run it on the one that has the lowest noise level, then there might be many jobs ahead of you. But in quite a few cases, I got the result almost immediately. So it ran almost immediately.
Thanks.
Yes.
Yeah, so about the queue time, during summer vacation when there are a lot of intern students, the queue time increases. But in the rest of the year, the queue time is almost, there is no queue time. But during the summer vacation, it can go for 2 days or 3 days, the queue time. Yeah.
Questions? If not, then let us thank Joachim again. And we have refreshments served at the back of the auditorium. But before leaving, we would like to present him with a memento from the institute. And I think it should be somewhere here.
So, thanks a lot. Yeah, thank you so much. I really appreciate it. I really appreciate being here and having had a chance to talk to you about neutrinos.
Okay, I think we can break for coffee.